Welcome to Maths with Bob. Today we're looking at applications of calculus to the physical world. This is a projectile motion problem which is reasonably complicated because we're experiencing air resistance now, which is actually proportional to both x's and y's, and it's actually proportional to the velocity. So how I set the equations up originally, I think this is the best way to do it, is like this. You just draw a picture, okay, here we go, we are projecting something up, okay, velocity v, angle alpha, and we know, it has, we've got y dot and x dot here, okay, initially, okay, and we know that there's actually a force, so there's something resisting the force, okay, so there's actually a resisting force, okay, this is the resistance, okay. Now, it actually has components as well, okay, and we're told that these components are in fact basically proportional to the velocity. So we will actually say that this is actually what kx dot acting that way and ky dot acting that way. So our equations of motion, okay, will be, we know that gravity is acting, so let's actually have a look at the equations of motion. Okay, so let's just try the equations of motion. Now these are going to be a bit more complicated now. Okay, so let's have a look. Okay, okay, so what about the y? What's happening in the y direction and the x? Well, now y double dot, we'll just start y double dot. Okay, we know there is a minus g, but there's also, if you have a quick look, not only is gravity acting downwards, but we have also this, like, ky dot minus g here. And we know g is actually 10, so let's just write 10. Okay. That's right. Okay, so we know that gravity is acting down. Okay. And the resistance is actually acting in that direction initially as well. So 10. Okay, so, so 10. Okay. How about the x double dot? Now, usually x double dot in projectile motion is actually equal to 0, but you can see in this case we actually have, there is something resisting as in the x direction. So this is actually equal to minus kx dot. Okay, now we're now going to have to try and solve these. This is starting to get a little bit more complicated. We can actually see, hopefully over here, that this is actually this is a growth and decay type situation. You have the rate of change of velocity. So you've actually got something like this. You've got here, you've got what dv dt is actually equals minus kv. So we know straight away that, okay, what's the solution to this? Okay, well, v is actually the x component, I guess I should say. Vx, isn't it? Let's just put an x there, which is just called x dot if you want. So what x dot would equal what? A e to the what? Kt. Okay, k is negative, so let's actually write minus kt here. Okay, so we know that, okay, this will be actually a solution to this, okay. We know that basically that it's actually decaying, okay, and this is actually like a growth and decay equation. We can actually do that a different way. You can do it like, write it like this, I suppose. You can actually write it, but whatever way you write it, you'll get the, okay, let's have a look. You can write it like this. X, okay, double dot, okay, is equal to minus k x dot, and you know this is really like dx dot dt equals minus k x dot. Okay, you can then sort of try and separate the variables, but I think can solve it, turn upside down, do other things, but I mean, we should recognize this as a growth and decay type situation where the rate of change of the velocity is actually proportional to the velocity in the x direction. So I'll just write this as x dot is equal to some a e to minus kt. And you know that a will in fact be, well, t is equal to 0. It's just what? What is it? What is a? Okay, so a is coming through this way. So a, the x dot component is the coming through the angle. So x dot is equal to what? V cos alpha initially. So at t is equal to 0. X dot is equal to a, so in fact x dot, you can see here, x dot is equal to what? V cos alpha, e to the minus kt. Okay, so that is what x dot is. Now, y dot is going to get a little bit more complicated because we need to solve this differential equation as well. This for y dot. Okay, so what are we going to do? Well, let's have a look. dy dot dt, okay, equals minus k y dot minus 10. Let's turn it upside down. Dt, or take the reciprocal on both sides if you like. Dy dot equals what? 1 over negative ky dot minus 10. Okay, multiply by dy dot, dt, and put the negative sign on the other side. Okay, minus k equals what? Dy dot over, okay, ky. No, this is now positive. Okay, and hopefully we can see that's a log, so we end up getting, okay, what? If you like, minus t is equal to what? Put in the k, so it's 1 on k, okay, ln, what? Ky dot plus 10. Okay, plus a constant. Now the constant, obviously, when t is equal to 0, we know, what do we know when t is equal to 0? Well, when t is equal to 0, we know that y dot, okay, is just v sine alpha. That's not too bad, that's the initial component of the velocity. Okay, so we now need to try and put that in and find c. So, okay, let's put it in. T is equal to 0. Okay, therefore 0 is equal to, okay, 1 on k. Okay, now we have a ln. Okay, now we've got to put in the v. This is y dot, so it becomes k, now v sine alpha, okay, plus 10, plus the c. So we know that the c, okay, the c would actually just equal minus 1 on k, ln, this expression here, k v sine alpha, plus 10, okay. Therefore, what? Putting it back in, we know that minus t is equal to 1 on k. Let's take the 1 on k out. Okay, we have a ln ky dot plus 10, but we've also got a minus here, ln, you can see here, kv sine alpha plus 10. Okay, will it fit in? Might just fit in on the end there. Okay. So we can see we just multiply by k. Now we get what? Minus kt is equal to, combining the logs, ln, you can see here this has got ky dot plus 10 all over, using our log laws, kv sine alpha plus 10. Okay, raise everything to the power e, we end up e to the minus kt is equal to what? Ky dot plus 10 all over kv sine alpha plus 10. And that's pretty easy now to rearrange and make y dot the subject. So that's what we're going to do now. So we're just going to now make y dot the subject. So let's see what happens. Now from there we actually integrate again, obviously, to get the x's and the y's. But let's go through this. We end up what? Okay, we have e to the minus kt times this expression. Okay, k v sine alpha. Okay, sine alpha plus 10. Okay, and that's equal to what? Just ky dot plus 10. So you can see here now it's pretty easy now to rearrange this for y dot. What do we end up getting? We need what? Y dot is going to equal what? Okay, first of all, let's actually write it as ky dot to start with. Ky dot is just what? E to the minus kt, kv sine alpha plus 10 minus 10. Okay, and divided by k, so we end up getting what? Y dot is equal to what? 1 on k, lots of e to the minus kt, kv sine alpha, plus 10, close bracket, minus 10, close bracket again. Okay, so this is now our, if you like, our y dot. And what was our x dot? If you remember what our x dot was, okay, x dot, remember, was just the cos alpha, okay, the e times e to the minus kt. Okay, this was our, if you like, our x component. And we now have to integrate both those two expressions back to try and find out what our x and y are. Okay. Okay, so what is this constant? Well, you can see here, if y is 0, we have 0 equals, now, minus 1 on k, that's e to the k, actually, I think it's minus kt there, whoops. Okay, it was, if t is 0, that's just 1, v sine alpha. Okay, we got minus 10 on k squared times 1, and, okay, and then we also have a 0 minus 0 plus a constant. Okay, so we now know that the constant is just what, 1 on k v sine alpha, okay, plus 10 on k squared. And this is our constant, which we need to put into the equation, okay, to get the y value. Okay. Okay, we're now going to try and find the maximum height reached, and we know we have to set y dot to equal 0. And basically, if y dot is 0, you can see here y dot is 0. Okay, we can therefore basically, what, e to the minus kt times this expression k v sine alpha, okay, plus 10, okay, is going to equal 10. Okay, so we just divide by, so we get what, e to the minus kt is equal to what, 10 over this expression, kv sine alpha plus 10. Okay, and now, okay, I can find the time now by taking the logs. Okay, so let's just take the logs. So what minus, I just do this in one step, minus kt is equal to the ln of this expression. Okay, now, just while I'm here, how about we, okay, we can actually use the negative sign to switch that around. So how about we just make this a positive kt, use the negative sign in the logs to make that kv sine alpha plus 10 over 10, to swap that around. Okay, and then you can see the time is just what, 1 on k, this log ln, this expression, okay, kv sine alpha plus 10 on 10. Now, so that is the time it takes to reach its maximum height. Okay, and if we have a quick look, I've just basically got it in GeoGebra here. You can see here the maximum height is actually over here. Okay, the maximum height. Okay, all right, we'll have a look at this again in a minute. If you just go back and have a quick look, that was just x is equal to, it should be back here, here we are, v on k cos alpha. That is our limiting position. Oops, we still have a remnant from the other screen here. I'll just try and rub that out. Okay. All right, now, okay, we now need to actually, if you like, get t in terms of x and substitute into y to actually get our, if you like, equation of motion. This does take a bit of work. Okay, so first of all, we have to rearrange our this expression here, okay, to make t the subject, and if you do that, you should actually get, I won't do that all here, but I mean, hopefully we can just rearrange that to make t the subject. T is equal to minus 1 on k, okay, is going to be ln, okay, 1 minus kx over v cos alpha. Okay, now that is the expression we need to substitute into the y, so into all these expressions here. So you can see it's going to get a little bit tricky. That time has to go here. Okay, obviously wherever the time is here. Okay, here as well. Okay, and also, is that it? Yeah, okay, it's only 3 spots. Okay, we need just to substitute that into 3 spots. And what I found the easiest way to do it was just basically try and get an expression with minus kt. Minus kt is going to be quite easy to get, and if you just see here, like, so we've got what, minus kt, you can just see here we can rearrange that and get an expression in terms of logs, and as you know, logs and exponentials are inverse functions, so that's going to drop it out quite nicely. Okay. Well, okay, here's the equation of motion. You can see here we put time in terms of x into the y expression in terms of time to generate this massive equation for the y position. This is called the equation of motion. And if you have a look in, I'll just show you in GeoGebra, it was a fairly, there it is at the top there, on the top line there. It's a massive function you can see here. That is the actual function. Let's actually just have a quick look at a couple of things on this too while we're here. Okay, you can see here I've actually marked the intersection of the x and y max values as max there. If you can see here, if I can actually start to change my velocity. You can see here I'm changing my velocity up to about 290 meters a second. Okay, if I drop it back to about 40, which is what we were kicking the soccer ball at, let's have a look. 40, there we are. So you can see here that actually the soccer ball has been fairly affected by the resistance at 40 meters a second. Now you can actually change the angle which you kick the soccer ball. I'll just show you. Let's actually start kicking the soccer ball higher. Okay, then a bit lower, and you've got the you're going to control the actual resistance constant, if you like. Oops, disappeared. And you can see here. Okay, we've got. Let's actually start changing the velocity up a bit higher. Okay. Okay. So you can see here that actually it was quite a complicated problem, this one, actually. And well, that's all for today, and thank you very much for watching. Bye for now.